Okay, so as I had mentioned, we're in Chapter 7, Differential Equations, and we've looked at differential equations from several viewpoints. One viewpoint was looking at the direction field of a differential equation. Based on the direction field, we can see qualitatively what solutions would look like given different initial values. And then, of course, we learned about Euler's method, which would allow us to approximate solutions to differential equations, initial value problems. And then, of course, in section 7.3, we learn about separable differential equations. And separable differential equations are ones where you can separate the variables and solve explicitly. Usually, you can solve explicitly for for y. Okay, and you actually saw in 7.3 some different applications of differential equations, and those applications, those models, those differential equation models that you saw in your homework for section 7.3, those differential equations were all separable. And that's one beautiful thing, is that some very beautiful applications in math involve separable differential equations. Chemistry also, you can do chemistry as applications of separable differential equations based on the law of what's called the law of mass action. So you're gonna see more examples. Like if you take Math 282 differential equations in that course in the spring, you'll see more applications of differential equations. But at least you're getting to see some here in chapter 7. And section 7.4 deals with exponential decay. Okay, so let me kind of like to highlight things here. So one of the models for population growth that you already saw in section 7.1 was that the assumption that the population grows at a rate proportional to the size of the population. In other words, dp dt equals k times p. And we always need to, when we propose a differential equation for a when we want to model a situation using a differential equation, we have to ask, is the assumption reasonable? Okay, and they talk about bacteria. Okay, they talk about bacteria here, and they're saying for bacteria growth in general, it seems that the growth rate would be proportional to the population size. Okay, so for instance, in restaurants have to be very careful in their food handling practices because bacteria can grow very quickly, and it can be deadly, to people if they eat, E. coli bacteria, for instance. Bacteria could be modeled with using exponential growth. That is a good example. And they talk about exponential decay as well. And do any of you remember from your pre-calculus days an application for exponential? Well, what would what would model, what would we want to model with an exponential decay model? Okay, exponential decay models situations as well. We can model growth exponentially for bacteria. Where would we see exponential decay? Okay, good, Noah. So half-life of an atom. So isotopes, radioactive isotopes decay exponentially. Okay, and you have seen some of that in your pre-calculus. But of course, in pre-calculus, you just worked with an equation, but you didn't know where the equation came from. Well, you're going to see here where that comes from. So going down here, they talk a little bit more about, well, here they mention, nuclear physics, radioactive substances decay at a rate proportional to the mass. Okay, and then also in finance, the value of a savings account with compounded interest increases at a rate proportional to the value. So we have here then the general formula. Well, in general, if y of t is the value of a quantity y at time t, and the rate of change of y with respect to t is proportional to its size, then at any time dy dt will equal k times y. And they call this the law of natural growth or natural decay. And the question is, let me ask you, is this a separable differential equation that you see here? dy dt equals k times y. Is that separable? That's right, Michael. It is separable. That's right, Rodrigo. It's a separable differential equation. So we're going to get a solution for that differential equation by separating the variables. So they show here how to do it. It's not hard. So if you separate the variables, you're going to have so I'm looking in this box here, you're going to have dy, or 1 over y dy equals k times dt. Okay, if you separate the variables, and I know you can do that. And then you integrate both sides. And on the left side, you're going to get the log of the absolute value of y. And then on the right side, you're going to have kt plus c. Well, of course, we want to solve for the absolute value of y. And we exponentiate both sides of the equation. We have the log of the absolute value of y equals kt plus a constant of integration. Well, I got to be careful. That's just a constant, but it relates to the constant of integration on the left and the right side. But we just put one constant on the right side. Now we exponentiate that equation. So the absolute value of y equals e to the kt plus c power, which can be written as e to the c times e to the kt. But then we'll let e to the c equal a. So, and we can drop the absolute values because y is going to be positive in these applications. Populations, amount of isotope left, that's positive. So, well, I got to be a little bit careful here. Actually, hold on that. What they do is they let a be plus or minus e to the c, and that allows the absolute values to be dropped. But that's fine. That's fine. So here then we have a solution at y equals a to the e to the ktth power. That's the solution to our differential equation, dy dt equals k times y. But we want to solve for that little constant k there, right? We have to solve for the little constant k. So at time 0, y of 0, okay, at time 0, y of 0 would equal, so we're going to solve, well, I want to be a little bit careful here. It's not the k we're going to solve for. Wait, hold on. Just give me a moment. Give me a moment here. One moment. Okay. So y of 0 equals a times e to the k times 0. And that equals a. So that means the value of a, that a constant, is just equal to the initial value y of the function. And therefore, the solution to the initial value problem here, the solution to the initial value problem, dy dt equals k times y, where y of 0 equals y naught, the solution is going to be y of t equals y sub 0 times e to the k-teeth power. Okay. Y of t equals y to the 0. I want to be a little bit careful. Let me rephrase that. The solution to the initial value problem is y of t equals y sub 0 times e to the k-teeth power. Now, how many recall that formula that I have highlighted in pink? How many recall similar looking formula in pre-calculus when you studied exponential decay, exponential growth? I mean, that's a very common topic in pre-calculus. How many recall using that formula in pre-calculus? Okay, Justice remembers it. All right. Tina does not, but Michael does. Okay. Well, you know, Eric does. Eric does. All right. And I appreciate all your input. So that formula is one that certainly some of you have seen in pre-calculus. But in pre-calculus, what would happen is you would reach the let me just see here. One moment. I actually have the pre-calculus book. I would actually have I have the pre-calculus book right here with me that's used at Montgomery College. And let me just see, one moment here. One moment. One moment. Okay, hold on, everybody. What I'm doing is I'm going right to the section in the book on that. So, you know, in pre-calculus book at Montgomery College, they have a section on exponential growth and decay models. And what they do is right off the bat, you know, right at the beginning of the section, they give you this formula that y of t, in pink here, y of t, the amount at time t equals the initial amount, y naught, times e to the k-teeth power. But they, of course, don't tell you where they got that formula from. But now you know, because we actually derived the formula as you see right here. We derived it. Okay, because in calculus we can derive things, and you know now where this formula comes from. All right? Are there any questions on that? Any questions? All right, all right. Well, why don't let me go ahead and then bring up an example here. I mean, let's do an example. Okay, so here is an example. And I want to give you a little time to copy this example down, and then we're going to solve this example. Okay, so I'm right here. Give you a little more time to copy the example down. Okay, so Noah threw out a guess there in the chat window about what the answer was. Well, Noah, you're not far off, but not quite right. But let's see. All right. Well, let me go ahead here and sort of discuss the problem here. So, common inhabitant of human intestines is the bacterium Escherichia coli, E. coli. Okay, how many have heard of E. coli before? Hopefully you have heard of it and had an, okay, all right, and thank you. And it says a cell of this bacterium in a nutrient broth medium divides into 2 cells every 2 minutes. Okay, so 1 cell divides into 2 cells every 20 minutes. And the initial population of a culture is 60 cells. So what we want to do is we want to find an expression for the number of cells after T hours, and then find the rate of growth of this bacteria population after 10 hours. Okay, so, all right. Okay, so does anybody need a little more time to copy the example, or are we good? Can we move forward? Okay. Okay. Okay, well then let's move forward here. So what we're going to do is we're going to let y equal the population, P-O-P, I mean population, of course. Population, you know what I mean. There. Okay, so let y of t equal the population of E. coli after T hours. And now, is the rate of growth, we have to ask the question, is the rate of growth of this E. coli population proportional to the size of the population? And the answer is yes. Okay, so for these bacteria populations, that's true. Okay, and actually the fact that the 1 cell divides into 2 cells every 20 minutes, so after 20 minutes you have 2 cells. You start off with 1 cell. After 20 minutes you have 2 cells. After 40 minutes you'd have 4 cells. Okay, after 60 minutes you'd have, how many cells would you have after 60 minutes? So 1 cell divides into 2. 2 cells divides into 4. Okay. 4 cells would divide into 8. 8 cells divide into 16. Good. And 16. So then 16 cells into 32 cells. So this type of growth is equivalent to saying the rate of growth is proportional to the size of the population. It is exponential growth. So that means then that we know that dy dt equals k times y, and our initial population is 60 cells. Now what I did on the right here is basically, it's what the book did. Okay, it's what the book did. The book derived the formula. Of course, their formula was y equals a times e to the kt power. Well, I have y equals c2 times e to the kt2 power. So you don't need to copy this down, what I'm highlighting in the red, because it's there in the book. But I'm just showing you, I'm just, reminding you that, hey, given this differential equation here, we can solve it. We can solve it. And so y of t, the amount of bacteria at time t, is going to equal 60 times e to the ktth power. Okay, and what we have to do is we have to find this relative growth rate k. Okay, the formula is not useful to us unless we can solve for k. K is called your relative growth rate. So we have to make use of the information in the problem. After 20 minutes, the population of 60 cells would become 120 cells. Because every cell, after 20 minutes, every cell divides into 2 cells. So if you start off with 60 cells, it's going to then, after 20 minutes, you're going to get 120 bacteria cells. And incidentally, why aren't we putting, we're putting 1/3 in here for our time. Shouldn't we put 20 in there? Why are we putting 1/3? That's right, Michael. It's in hours. Remember how we define y. Y was the population of E. coli after T hours. So that means when we use the formula, time has to be in hours. Well, 20 minutes is 1/3 of an hour. Okay, so of course, now I'm going to solve this for K. And you've done this kind of problem many times in pre-calculus. How many recall doing this kind of thing in pre-calculus, solving for that relative growth rate K? Yeah, you know what I mean. Michael knows what I mean. You, Snega, you've seen it, sure. So, we'll divide by 60 both sides of the equation here. So 2 will equal e to the 1/3 K. That's not a negative there. It's just 1/3 K. And then we take the log of both sides of the equation, and K will equal 3 times the log of 2, which is the log of 2 to the 3rd power, which is the log of 8. And now wonders where we got the 120. So this E. coli bacteria, each cell divides into 2 cells every 20 minutes. Okay, so we started with how many cells? We started with 60 cells. So after a third of an hour, the number of cells that we would get would be 120 cells, because each cell divides into 2 cells after a third of an hour. So 60 cells becomes 120 cells. Nothing else good on that. And then Tyreek wonders how we got the third. Well, we have a third here because our time in this case needs to be in hours, because that's how we define our y. Y was the population of E. coli after T hours. And so we, instead of putting 20 minutes, we put a 1/3 of an hour. All right. So K is the log of 8. And now we're going to put in, for K, the log of 8. But we want to write this I mean, this WebAssign would take that answer. Okay, but why would you leave it that way? Why not write it in a prettier form? So e to the log of 8, you can separate. Well, I want to say this the right way. So your power is the log of 8 times t. But e to the power log of 8t is the same as e to the log of 8 power raised to the tth power. Okay, it's the same thing. And it's good to do it that way because e to the log of 8 becomes what? It becomes 8. Okay, so now you have that y of t is equal to 60 times 8 to the tth power, where t is greater than or equal to 0. And WebAssign might want the answer in this form. It might not take the answer in the first form. I'm not sure, but it's no big deal because really you want to get it in the second form anyway. Okay, so now we have a formula for the number of E. coli, the number of cells after T hours. Are there any questions? All right, well, then the next thing that's asked for in the problem is find the rate of growth of the E. coli bacteria population after T hours. Find the rate of growth. When you think about rate of growth, what do you think of? A rate. What is a rate in calculus? That's right, Rodrigo. One moment. Hold on, one moment. That's right, Rodrigo. That's right, Tina. A rate is a derivative. So the rate of growth, well, I could differentiate my formula, right? Y of t equals 60 times 8 to the tth power. I could differentiate that formula and get dy dt. But if you've noticed, we already know that dy dt, well, hold on, let me put a little aside here. One moment. There are things here that aren't, this here at the top isn't. Well, I know why I wrote that. But so, right, dy dt, the differential equation that models bacteria growth is dy dt equals k times y. Okay. And well, k, we learned, was the log of 8. That was our relative growth rate. And y, we just found what y is. That equals 60 times 8 to the tth power. And so dy dt is equal to 60 times the log of 8 times 8 to the tth power. I mean, that's pretty cool, right? We have rather than taking the a fresh derivative, we know what dy dt is. And we just substitute in the k and substitute in our solution y. And that gets us there. So after 10 hours, dy dt, okay, dy dt, evaluated at t equals 10, we just plug in the 10 for t equals 10. So we're going to get 60 times the log of 8 times 8 to the 10th power. Okay, now try typing, hold on here. Try typing that on your calculator. And you're going to get 1.339670001 to E11. Okay, how many are noticing that? I mean, maybe try it on your calculator. I think it would be good to do at your homes there. Michael got that. So your calculator gave you 1.339670001 to E11. Well, what's that mean in calculator notation, the E? What's that stand for? It's got to stand for something. Okay, what kind of notation is that? I'm seeing it. You're right. That's right, Cologne. Scientific notation. So that's the calculator. You know, the calculator, that's a lot of zeros to carry, you know. So this is 1.3397 times 10 to the 11th power, and the units are cells per 1 hour, cells per hour. Okay, and then if we write out the, well, you know how to work with scientific notation. You're going to move the decimal place here, this decimal point. How many, 1.3397 times 10 to the 11th power. You move that decimal point, how many places to the right? That's right, Tyreek, 11. And so you're going to get 133,970,000,000 cells per hour, which is 133.97 billion cells per hour. After 10 hours, that's the growth rate for this bacteria. How many think that's absolutely amazing? Well, would you regard that as a pretty fast growth rate? Absolutely. Absolutely. Nature doesn't wait around, you know. Yeah, and this is another reason, again, why these restaurants, they have to be very careful. Oftentimes if, the restaurant will get closed down if they have an outbreak of, something like this. Well, Not Now asks a good question. The reason I wrote the final answer as 133.97 billion cells per hour is because it's a little more intuitive to me. It makes me appreciate how fast this growth rate is. But also, WebAssign will want you to write. You'll have a problem like this, and they will say write your answer in as billion cells per hour. So that's why I did it that way. All right, Not Now, good. All right. Well, are there any other questions before we move on? Okay. Well, let's go ahead and look at another example. Okay. This example has to do with a topic called Newton's law of cooling. How many have heard of Newton's law of cooling? Okay, Rodrigo remembers it. Michael has. Okay, well, let me give you a moment to copy this example down and we'll go over it. Salome has. Yeah, Tina, Newton does have a law for cooling. Yep, yeah. And you're going to see it in a moment. All right, I'll let you copy the example down. Take a moment. Okay, so let's take a look here. We have a bottle of soda pop at room temperature. And you take this bottle of soda pop and you place it in a refrigerator where the temperature is 44 degrees Fahrenheit. Okay. After half an hour, the soda pop has cooled to 61 degrees Fahrenheit. So the question is, how long does it take for the soda pop to cool to 50 degrees Fahrenheit? You know, how many notice that soda pops tend to taste better, like a, Coca-Cola or Sprite? How many feel that they taste a little better when they're cold? Okay, Tina agrees, and Justice does. And how many have had a situation where, Eric, definitely. How many of you had a situation where you put a soda, a can of soda in the fridge, it's at room temperature, and you're wondering how long is it going to take for that to get cold? Maybe you don't have any cold soda pops in the fridge, and then you got to put one in, and then you got to wonder how long to wait. How many have had that situation? Okay, Michael a lot, Tina, Marcella, yes. Well, now you see you'll be able to find out how long it's going to take for the soda pop to cool a certain amount. All right, so let's go ahead and move to the solution if we're good here. So we need a differential equation that will model this situation. So we're going to let T, capital T of T, be the temperature of the soda pop after T minutes. Okay, we always have to define we know little t is time, but we should define our dependent variable also. And we're talking T, capital T is the temperature of the soda pop after T minutes. We're not doing hours, we're doing minutes. Because it makes more sense in the problem, right? Now, by Newton's law of cooling, the capital T dt is equal to K times capital T minus 44. Okay. So this means, well, one moment. Let me give you a moment to copy that down. Well, Tyreke Newton came up with this equation, or him or his associates. This is one that you just need to know. By Newton's law of cooling, the rate at which I want to say this the right way. One moment. Okay, so what I'm doing is I'm in your book, in your textbook, in section 7.1. If you look at the 14th exercise in section 7.1, they mention about Newton's law of cooling. And Newton's law of cooling, I'm just reading right from the exercise, and this is what the Diffie-Q says. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, provided that this difference is not too large. So the again, let's sort of the hold on here. The rate of cooling is proportional to the difference between the temperature of the object at time t and its surroundings. Well, you're putting the soda pop in the refrigerator, so the surroundings are 45 degrees for the soda pop, 44 degrees Fahrenheit. Okay, so does that help, Tyreek? Help you see where how we got this differential equation? Does that help? So that's, I mean, Newton's law of cooling. Okay, all right, yeah, that Newton's law of cooling is stated in that exercise 14 in section 7.1. From there, we can construct the differential equation. But all the differential equations, are going to be similar for Newton's law of cooling. And what we have to do is we have to solve for, we're wondering what is the formula here. So there are several ways to do the problem. But one way is to just solve it, using separation of variables. And if we do that, I separate the variables here, and then I integrate both sides. Okay, and I go through the steps here. And I'm going to get that the temperature at time t is equal to 44 plus constant times e to the kth power. Okay, that's what you're going to get. Okay. So, I don't want to like verbally state every little part here, because I know you've seen this. You know how to do the algebra and stuff. Are we okay up to the last step here? Are we okay? I mean, up to this step? Are there any questions? All right, so now in this case, we have two constants. Let's see, when do we know t is in hours and when t is in minutes? Well, the way you know that, Tina, is in the context of the problem. I guess, well, I see what you're saying, because here they were talking about hour. It's an hour, right? Like, they're given the problem, they're saying after half an hour. I guess what would happen is in the problem, if they say, like, give your answer in minutes. I mean, look, we could have let's say it's the right way. We could have defined our temperature T to be the temperature of the soda pop after T hours. We could have done that. I just chose to use minutes. But, so long as you're consistent throughout the problem. So, I mean, what's going to happen is, of course, we're going to get an answer in terms of minutes, but then we'll convert it to hours. Okay. All right. Does that? And here now we have two constants. We have the constant c, and we have this other constant k, and we have to solve for those. So we need two pieces of information. Well, the first piece of information is after 0 minutes, T is equal to 72 degrees Fahrenheit. I mean, right when you put the can in the fridge and when you just put it in, the can's temperature is 72 degrees Fahrenheit. So that means then if we put 72 in for T, okay, and then for capital T, that's temperature, and then 0 for lowercase t, we can solve it, and we can get that 28 equals C. And so our temperature function for the temperature of the soda can is going to equal 44 plus 28 times e to the kt power. So far, are we good? Okay, so now we have to solve for that little k constant. And I wanted to do this one with you because, you know, this one has two constants to solve for. So how are we going to solve for the little k? For this little k here? How are we going to solve for that? What piece of information do we need to use? That's right. That's right, Felicity. That's right, Rodrigo. After 30 minutes, the soda pop is cooled to 61 degrees Fahrenheit. So after 30 minutes, the temperature of the soda pop at 30 minutes is 61 degrees Fahrenheit. And so we plug T equals 30 in our T formula, our capital temperature formula, and we solve for K. And so the temperature of our soda pop after T minutes is going to equal 44 plus 28 times e to the negative 0.01663 T. And I use a lot of decimals because WebAssign is very picky on the constants and so forth. So, you know, you might even consider using the exact value here, but I don't know if that's necessary. So long as for that K constant, so long as you go out enough decimal places, you should be okay. But you have to go out enough, you know. And so now the formula for the temperature of the soda pop is completely specified. And should that value of K, you notice the value of K, we got as a negative. Would it be a problem if the value of K were positive? Would that be a problem? I mean, would that? Okay, Rodrigo says definitely. The value of K has to be negative. Why? What would happen, Rodrigo, if the value of K, you know, of this value here, if that were positive? Why would that be wrong? Why would that be wrong? That's right, Michael. It would be getting hotter. That's right, Felicity. Temperature would increase. Rodrigo knows, absolutely. So, you know, you see, that's one nice thing about these kind of problems. You can, you know, I'm thinking of your exam, you know, next week. You know, okay, you got 2 tries to get the answer right? So, you know, one tries for the typo, maybe a typo. The other try is, you know, trying to get it right. But you can sort of think about the reasonableness of your answer, right? Of course, that K should be negative. And now we're going to find out how long it takes for the soda to cool to 50 degrees. So 50 will equal 44 plus 28 times e to the negative 0.01663 t, and you solve that for t. And all this algebra, this is just algebra. You've done it in pre-calculus. Okay, let me give you a moment to copy it down. They're saying T is 92.6 minutes. Okay, so are there any questions up to this step here then? Are we good with that? Okay, well now let's put that in convert it to hours then. And so if we want to convert to hours, I think you can convert minutes to hours. The soda pop will cool to 50 degrees after about 1 hour and 33 minutes. Okay, so of course I took, well, I mean, I'll just be, hold on here. So if you take 92.6 minutes and multiply it by 1 hour, divided by 60 minutes. Let me just do it right here. Just using M for minutes here. So 92.6 divided by 60. Okay, hold on. That's going to be, well, that's 1.54 hours, roughly. Okay, but if you convert then that, so it's, you know, the 0.54 hours, you can convert that, well, you can convert that into minutes, right? By taking 0.54 and multiplying it by 0.5 hours, by multiply it by 60 minutes over 1 hour. And if you do that, you'll get 32.4. But what I have basically is 1 hour 33 minutes. So you know how to do this. You know how to do this. Are there any questions at all? Okay. And another thing too, I'll come back to this page, but notice that based on your temperature function, what happens to as time gets longer and longer, if you let the soda pop in the fridge for days and days and days, okay, time, T, in minutes gets more and more. What happens as time T gets large? What happens to this? What happens to that term? The 28 times e to the negative 0.01663 t. What happens to that term as t gets large? What does that second term approach? That's right, Michael. That term approaches 0. And so what happens is that, because, you know, the exponent is going to be very negative, and e to a negative infinity is equal to 0. So this just means that, you know, I mean, what I've done is I drew a graph. This is from the book, but there's a graph of our temperature function. Starts at initially at 72 degrees. That was the temperature of the room. But, you know, we put it in the fridge, it's at 72 degrees, and then it cools down, but never goes below 44, which makes sense because the fridge is set at 44 degrees Fahrenheit. Okay. So how many may like in terms of soda pop cooling to 50 degrees Fahrenheit, how many have noticed that, yeah, it takes about an hour and a half for that soda pop to cool to maybe 50 degrees Fahrenheit, something that, you know, is like cold, reasonably cold. How many have noticed it takes at least an hour? Oh, Tina says put it in the freezer. Won't it freeze, Tina? Won't it freeze the soda? Or will it? Right. Oh, I see. So it won't, like, I never thought about that. All right. Well, you know. All right. Are there any less time overall good strategy? All right. So but you have to take it out in time. All right, from the freezer. All right. All right. Right. That's what I was worried about, Justice. The can expanding or bottle shattering. You know, we don't want that. So now let me just show you how the book does this problem. Okay. Let me show you how the book does this problem. I want to go into the book. I think it's important that you see it. See, you can take this problem. You can take this problem and actually rephrase it as an exponential growth problem. So what they do is, you know, this is actually, I worked out example 4 from the textbook, section 7.4. But what they do in section 7.4 is they work out the same problem, but they rephrase the problem as an exponential, well, decay problem. So what they do is they say, look, let y, I mean, here dt is k times t minus 44. What if we were to let y equal t minus 44? Okay, well, dy dt would equal dt, right? So the differential equation here could be re-expressed as dy dt equals k times y, but your initial temperature would not be well, you're not doing like temperature, you know, to get the value, the initial value of y, since y was equal to t minus 44, y of 0 would be t of 0 minus 44, which is 72 minus 44, which is 28. So what they do is they rephrase Newton's law as an exponential decay model in pink that you see. And then you know you have a general formula for exponential decay models at y of t equals y at time 0 times e to the kt. And so then that'll equal 28 times e to the kt. And then you can solve for k. Okay, you can solve for k. But we have to convert everything. So like after 30 minutes, when the temperature of the soda is 61 degrees, you have to adjust that initial condition by subtracting 44 from 61 because you've defined y as t minus 44. So after y sub 30 would be 17. Okay, so you have to like, so in one hand you have the problems. What they've done in the book is nice because they've written the Newton's law of cooling as this exponential growth model in pink. And so then you know the formula for the solution for an exponential growth model. But then you have to convert, make sure your initial conditions are being changed also to reflect that you're, solving the formula with respect to like y of t. And then once you get y of t, you'll get y of t equals, hold on, you'll get y of t equals 28 times e to the negative 0.01663t, but then capital T, the temperature function, would be 48 plus 28 times e to the negative 0.01663t. Okay, so, I mean, how many like this approach? It's a second approach. And I guess it's the approach that, since the book, I mean, either approach is fine, but how many like the second approach? How many like the first approach, the way that I showed you? I think there'll be a difference in feelings. Tina likes the first approach. Well, well, Michael, the second approach is the way you do it in pre-calculus. That's right, it is. But you see that formula that they use. Remember, the formula here in pink comes from the fact that we separated the variables originally on the differential equation and got a general formula. But yes, let me see a few more chats here. Okay, Eric likes the first. All right, so I wanted to show you two ways. All right, very good, very good. I want to show you something else too here. I want to show you another problem here. So I'm gonna look at a third problem, but this will be right from the book. This has to do with population growth, okay, and with the table. So in this is actually example 1 from the book. All right, and assuming that the growth rate is proportional to population size, use the data in table 1 to model the population of the world in the 20th century. So, the book was, we're in the 21st century now, but this problem, the book has been around a long time. So, so what they have here is they have a table with years and U.S. population in millions. Okay, that's what they have. And they want you to, they want you to come up with a model for the population based off the data. So since they're saying we can model population growth exponentially, human population growth, modeling it exponentially, I will tell you it'll work for a while, but it would not work forever because there's limited resources and so forth. Human population can't keep growing exponentially. But let me see here. Now, I'm looking here. They say here that we know from 2, let me click on that. We know from 2, oh, that's kind of cool. I click on that. We know from 2 that the solution is equal to P of t equals 1650 times e to the kt. Well, you see dp dt equals k times p. Okay, well, and the initial population is 1,615 million. That was in 1900. But they're not like having millions. Your units are in millions. But the differential equation and the initial condition, well, we know from we know that that fits the model, and so y of t is going to equal y sub 0 times e to the kt. So p of t will equal 1650 times e to the kt. 1650 is our initial population. Okay, so hold on here one moment. I want to click that off. Good, okay. And so they get the model that way. But you have to solve for K. You have to solve for K. So what they say is, well, let's use one of the years. Let's use 1950. If we use 1950, in 1950, the U.S. population was 2,560 million, okay, which is 2.56 billion, all right? And I believe the U.S. population is over 3 billion now. So they use then that P of 50 equals 2,560, and they use that and they solve for K. And they get 0.0087846, so the relative growth rate is about 0.88% per year. But they just chose to use 1950 as the second data point to allow you to solve for K. So if you choose different values, if you choose different data points, you're going to get different answers. And in your homework in WebAssign, they will tell you what data points to use, but you'll see you'll get different answers. Okay, you'll get different answers. And so, but what they do, let me see here, they then graph, well, they graph this population model. They graph it. They superimpose it over the data values. Okay, over the data values. So, like for instance, initially at time equals 0, the population was 1,650 million. Okay, and so based on, you know, this is 1,000, 2,000, 3,000. This the P scale, the vertical scale, is by 1,000. So they're starting at 1650, and then you know the data points are they're just plotting the coordinates. They're plotting the points from the table. Okay, it's a scatter plot. How many have done scatter plots before on their calculators? Okay, Justice has, and I'm sure many of you have. Okay, Michael, I'm sure many of you have. So let me ask you, the model does pretty well up till about what year? The t-axis is years since 1900. So the model, the purple model, our function P of t that we found, which we graph in purple, models the data up till about what year? Yeah, 1960, 1950, and then it doesn't do so well. Okay, it doesn't do so well, and so that's the thing you have to keep in mind about these models. They'll do well for a while, but they may not then do well, you know, after a certain number of years or a certain amount of time. And in fact, world population can be modeled using logistic growth model. You know, in other words, you know, could we come up with a model, you know, looking at that figure, could we come up with a model that would, you know, model the behavior correctly for the growth, the population growth up to like 2000? And the answer is yes, but it would be a more complicated model. So, so anyway, I thought you should see that, and that kind of model, logistic growth model, it is in our textbook, but it's an optional section. But if you take differential equations, Math 282, which I'm teaching incidentally next semester, if you take that course, you'll see how we can model, find a better model for this population growth. All right, so let me stop there for a. Let me stop there. Are there any questions at all?